Hey guys, so in this video, we're going to be talking about, and I may even say deriving, uh, one of our next big postulates of quantum mechanics. Um, physicists may yell at me for saying, I'm deriving a postulate, but we can actually sort of derive this postulate based on all the other postulates we've made. Um, and so this is called the expected values postulate. And expected values, hopefully that will sound familiar to you from our statistics video. If you have not gone and reviewed our statistics video in section 0, I believe it's 0.12 or 0.13, somewhere around there. This is the best time to go review that. It is incredibly important for this video, and unless you are, fresh off a statistics class, or you're really confident in your statistics, you'll want to know that for this video. And I'm actually going to start with some statistics. And this is the notation that we had in the last video. The expected value, or not in the statistics video, I mean, the expected value, and note these triangular brackets have nothing to do with inner products, even though you'll see you can actually express this with inner products. But these triangular brackets are just separate. They're something else. The expected value, the average value, right? Expected value is a bit of a misnomer, right? Because say I've got some observable that it can either be, value. It can either have the value 1 or 5, and I've got, if I have a probability distribution like this, right? Right, it can either be 1 or 5. Right? Its expected value, its average value will probably be somewhere over here, even though this is not actually a value that the observable can actually have, right? That's the average value, right? So the expected value is not necessarily the value. If I measure the particle, this is what I probably will get, right? That would actually be like the mode of the data set. The expected value is if I have a bunch of particles in identical states, right, and I measure their value of Q over and over and over again, right, each particle, if I average up all my results, this is what I'm going to get if I have enough trials, right? And this is, right, defined as, this is the sum over all possible values of j, right? Could be j equals 0 to, the number, but over all possible values of j times q sub j, right, the actual value, times the probability of having that value, right? This is how we define an average, right? The value times the probability of having that value. So this should hopefully make sense as a review from our statistics video, right? And now we're going to look at this with quantum mechanics. And well, really, I'm going to just start with this right here, right? We'll assume psi, right? Psi is equal to C1 V1 plus C2 V2 plus C3 V3 plus dot dot dot. Again, our normal thing where, and actually I'll write in an operator notation now, Q hat acting on phi sub Q is going to give us Q times phi sub Q. Right? What this is saying is phi sub Q is the state, right? Phi sub 1 is the state, for example, with big Q equals to little q1, right? Right, take the Hermitian conjugate, psi bra vector will give us C1 star phi1 bra vector. Right, we talked about this a few videos ago. C2 star phi2 bra vector plus C3 star phi3 bra vector plus dot dot dot, right? All right, so now we're going to look at psi inner product with q hat psi, right? And this is equal to, well, let's do this out, right? So C1 star V1 plus C2 star V2. I'm only going to do this with 2. You can see how it will expand with 3 or more, but just to save space, I'm only going to do it with 2. Times, well, Q hat acting on this, right? Well, let's, I'll write this out. So Q hat acting on, I'll just do these square brackets here. C1, V1, and again, this is plus dot dot dot. I'm going to erase this so I can actually add our plus dot 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 there. Times, right, Q hat acting on psi, which is C1 V1 plus C2 V2 plus dot dot dot. Right, and this is equal to, just write C1 star V1, right, plus C2 star V2, right, times, well, this is Q hat, remember, it's a Hermitian operator, but it's a linear operator. So when I act on the superposition, this will get me something like, C1 times Q hat acting on V1 plus C2 times Q hat acting on V2 plus dot dot dot, right? Well, now if I expand this out, right, well, expand this out over here, this is C1 star, right, still going to keep the same thing over here, V1, get my parentheses, plus C2, and I keep forgetting my plus dot dot dot, right, C2 star V2 plus dot 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 times, right, C1 times Q1, right, C1 times Q1, V1 plus C2 times Q2, V2, right, plus dot dot dot, right? So now I'm going to do, let's see, I think I'm actually going to have to rewrite this. So this is equal to, well, let's do a little bit of work up here, right? So to recap, I'm going to get rid of this for here. We're looking at C1 star V1 bra vector plus C2 star V2 bra vector plus dot 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 times, right, C1 Q1 V1 plus C2 Q2 V2 plus dot dot dot, right? Well, what we've got here, right, is if I just, FOIL this out, and you can if you want to try this with the third term, it will just make the algebra a little bit harder. I'm proving you to this with 2. You can see it will work with 3, it will work with 4, it will work with however many you want, right? So this is C1 star. Remember, these are constant multiples, right? So we can, these are constants and vectors, so we can actually take the constants out first, right? C1 star, C1, Q1, then phi1 inner product with phi1, right? Plus, now we've got C2 star, C2, Q2, phi2 inner product with phi, or sorry, well, I messed that up. That is a term, but I'm getting ahead of myself. So now if I take, right, we'll do C1 star C2 Q2, sorry, my bad, times phi1 inner product with phi2, right? Now plus C2 star C1 Q1 inner product of phi2 phi1, right? We're just foiling this out, right? Just like in algebra class. Plus, now we've got C2 star C2 Q2 phi2 inner product with phi2, right? And then plus dot dot dot, right? We'll have a term with C's, 3's, right? But notice, right, the term with phi1 and phi2, right, because we are assuming that this basis is orthonormal, because we know our good basis, right, in quantum mechanics is orthonormal, right? These terms are 0, and these terms are 1, right? So this is just C1 star C1 Q1 times 1 plus C2 star C2 Q2, right? Plus dot dot dot. And you'll see, right, if we had a third, right, the term with phi1 and phi3, and the term with phi2 and phi3, and, you know, vice versa, phi3 and phi1 and phi3 and phi2, right? Those inner products will all go to 0. So we're only going to be left with the terms, right, with phi1, phi1, phi2, phi2, right? So this would be, you know, we want to expand this. Right? Hopefully you see what I'm talking about. If not, go ahead and do the algebra, right? Add a C3 term, you'll see the same thing will happen if we assume, because we'll know, you know, phi3, phi1, right, is going to be equal to 0, and etc., right? And then phi3, phi3 is, so this is C3 star C3 Q3 plus dot dot dot, right? Well, what is this? This is C1 norm squared Q1 plus C2 norm squared Q2 plus C3 norm squared Q3 plus dot dot dot. Well, this is just summing up over all of our values of J, right? Well, what is C1 norm squared? This is, right, the probability of Q1. This is the probability of Q2, probability of Q3, right? So this is the probability of Q sub J, right? Because the norm squared of the coefficient is the probability times Q sub J, which if we look back here, right, just remember this result. Look back here, hey, right, other order, but remember multiplication is commutative, same thing, right? So this is equal to, sorry, see if I can, there we go, Q, so this is equal to the expected value of Q, right? If we look at this over here, right? We showed that this is all equal to this this summation, which is equal to our definition of the expectation value of Q, right? And so this is our next quantum mechanics postulate, and I'm going to just state it succinctly here. So hopefully you have all this down. Hopefully you did the whole, you know, the derivation or the proof or whatever you want to call it. Right? Just to write it down in short, any state psi, right, inner product with Q hat on psi is equal to the expectation value of the observable Q. So here's another cool thing that we can do with operators. The operator, if we know a particle is in a state psi, right, this is the expectation value Remember, expectation value is sort of a misnomer, but that's what we call it. It's really the average value. If you measure, you know, particles all in the state psi, if you measure them over, you know, one after the next, after the next, after the next, this is the average value, expectation value of the observable big Q, and sometimes this is written as the expectation value of the operator. I don't really like this notation. I'm not going to use it because either notation works. But actually, I think I may use this. It may just be easier to use for a few of the proofs that we do in this course, later in this course. But I don't really like this notation this much. I like this a lot better. But that's just a personal preference. So this is the expectation value of Q. Of the observable Q, remember. So big Q is the observable, Q hat is the operator, little q is the actual value. So this is the expectation value of Q for a particle in the state psi. All right. And so this is our expectation values postulate. Okay, see you in the next video.